Imagine being adrift in a dark ocean between galaxies. No nearby sun, no GPS, how would anyone find the way? Nature answers with pulsars, spinning neutron stars that beam like lighthouses and keep time like cosmic clocks. Their precise ticks can guide spacecraft across deep space and even help detect gravitational waves. A pulsar is a neutron star, the collapsed core after a massive star explodes in a supernova. About 1.4 times the sun's mass squeezed into a sphere roughly 20 kilometers across. A teaspoon of that matter would weigh billions of tons on Earth. A pulsar's magnetic field, up to 1 trillion times stronger than Earth's, rips particles free and launches beams from its magnetic poles. Because the magnetic poles are tilted relative to the spin axis, the beams sweep space like a lighthouse. When Earth lies in the path, telescopes detect pulses, blink, darkness, blink. As the core shrinks, it spins faster, conservation of angular momentum. Some complete hundreds of rotations each second, millisecond pulsars. Record holder PSR 1748 2446 add, 716 spins per second, surface speed near 1/4 light speed. Born from stellar death, these beacons also form a galactic map, a stable grid future explorers can use to chart where they are and where they're going. The most astonishing thing is their regularity. Pulsar timing rivals, and sometimes surpasses, our best atomic clocks. Astronomers can predict pulse arrivals years ahead, down to tiny fractions of a microsecond. If a pulse comes a little early or a little late, something along its path has changed. The first exoplanets were found this way, subtle, periodic tugs in the timing of PSRB 1257 plus 12. Monitoring a pulsar becomes a decades-long physics experiment with the universe providing the lab. That steady beat gives a baseline to measure tiny warps in spacetime. Pulsars slow down very slowly and predictably, so timing models can account for it. Millisecond pulsars, spinning hundreds of times per second, act like near-perfect celestial metronomes. Precision turns beacons into instruments. They reveal planets, probe interstellar gas, and test gravity, all through timing. On Earth, GPS uses precise timing from satellites to locate you. But far from Earth, GPS cannot help. Pulsars form a natural network. With an X-ray telescope, a ship can time several pulsars and find its position. Earlier than expected means closer to that pulsar, later means farther. With 3 or more, the computer triangulates in 3D. It can work from the Kuiper belt to the Oort cloud, even on trips to nearby stars. In 2017, NASA's sextant on the ISS used millisecond pulsars to autonomously determine its orbit. It worked. Gravitational waves are ripples in spacetime from massive bodies in motion. Countless pairs of supermassive black holes create a slow background hum with light-year-long wavelengths. Pulsar timing arrays monitor dozens of millisecond pulsars and look for correlated nanosecond timing shifts. In 2023, teams like Nanograv, EPTA, and PPTA reported strong evidence of this gravitational wave background. Thanks to pulsars, we now study the universe not just with light, but with gravity itself. Pulsars are more than dead stars. They are timekeepers and guides of the final frontier. Ride their rhythm into tomorrow. Subscribe to our Universal Universe channel for daily cosmic adventures. And don't forget to share and like the video.